almost zero. It's impossible to know that all the example or the input are covered. Today we will talk about a new tool, not new, a tool, maybe for someone new, to have in our toolbox to improve our way to cover more inputs for the function under testing. It's called property-based testing. Thank you. But let's start by the definition. We want property that are, we want to find property that are always true despite every input I throw to our function. So I want to be sure that whatever I throw to my function doesn't crash. So we have two main steps: finding good properties and having a way to throw input to our function. But as always, talk is cheap. Let's see some real code. Okay. No. There. Okay, maybe it's okay. Let's start with a simple example. We have this function that calculates the greater common divisor between two numbers, n and m. Doesn't mean the code doesn't mean a lot for us because it's just an Euclid algorithm from the book. How we can test this function? This is a classical unit test. So what we have a list of inputs, a list of expected results. So the GDC between 15 and 6 is 3, the GCD between 15 and 5 is 5, and so on. Classical unit test. We run the test for every input. We act, so we use our function and we have a result. We assert that our result is equal to an expected result. So we can run with PyTest this code, this test. Green. Sorry, it's small there. I can't zoom. I tried at home, but it's small, but it's all green. Trust me. So let's do another step. So we say that property-based testing have two steps. Let's talk about the first one, finding good property. What are the properties of GCD? We have our GCD must be greater than 0. D must divide n and m by definition of greater common divisor. And the last one is that no other number larger than n and m, larger than d, divide both n and m. These are the GCD properties from math book, okay? So we change a little bit the perspective. Someone of you maybe understood where we are heading to. Now the res, what the expected result, are gone away. So we found some properties about GCD. Let's see the second step of property-based testing, throwing random input to our function. I want to introduce you this, we are at Python Milano, so I want to introduce you this very cool Python library that is called Hypothesis. Hypothesis is the main library in Python to do property-based testing, one of the first, I believe, and give us a cool feature, the strategies. Strategy are generators that can generate different Python variable, different Python types. For example, here I'm calling an integer strategy, and I print 5 examples from the strategy. Let's run this. We can't see a lot, but let's try. Okay, It's a little small, but here I have 5 random integers. I can do something else, like max value 2, max value, I don't know, 500, mean value 2, and rerun. So again, I have some integer from 2 to 500. So why we can't use random.run, the classical NumPy or Python standard library number generator? Because I invite you to go to the hypothesis documentation is full of strategy, and I can make this strategy interact. For example, I want to generate a list of integer between 2 and 500. I can do something like that, lists. 5 lists of integer. I want to generate a list of tuples of integer. I have a list of tuples of integer. You can build, from the basic building blocks, I can build very complex input. So let's go back to our GCT and make another step. So here I want to introduce another keyword of hypothesis, is the given decorator. So what I'm doing here, I want to remove our example. If you remember, in our last test, we have some example. Here I want to remove it. I want send to my function random inputs. So for example, here I say, so given 2 integer, n and m, from 1 to 100, from minus 500 to plus 500, just for the demo. Given these 2, call my function and verify that all the properties are true. We can run this with PyTest. Notice that hypothesis is very well integrated with PyTest. Yes. No. Just a second. Okay. We have an error. We have an error. It's a little bit different on classical unit test error because it's hypothesis that what it does. It runs our test with a lot of couple of integer and search for some falsifying example. In this case, is small, sorry. We have, is saying zero division error. He found that there is an exception at zero division error, and the falsifying example is n equal 1, m equal 0. So I go back to my original function, and it's true. If n is equal 0, there is an assertion error. I forgot to check this case. So what I can do is very simple. If n equal 0, return m, right? By definition of GCD. Okay? And now it's green. So the point here is a very simple example. Of course, the point here is everyone know this control, but you can forget this control. And with classical unit test, you are limited because you can think many examples, also the 0 example, but you are not sure that you covered all the possible examples. But let's see another example. Let's zoom it a little bit. So here we have another more like business-like example with some classes and so on. We have a data class, a pizza class with a dough, with the toppings, with a price. We have some enum to take the type of ingredient, the type of dough. And we have this class called pizza generator that have just one method that generate a random pizza. So I have a max topping as an attribute. And my generate random pizza, what it does, generate a list of toppings a random DAV, and a random price. The last thing that we have in this code is a function that calculates the total price of a given order. So we pass an order, that is a list of pizza, and calculate the sum of the prices of the pizza. How can we test this code? I want to use property-based testing. Maybe, okay. Okay, what I'm doing here. Let's start with the code. I'm generating, I'm instantiating a pizza generator with a max topping. I call my method with a number of ingredients. I want to generate random pizza with an ingredient. I want to assert, and this is a property, a very simple property for the demo, that the length of the pizza topping are always less than max topping. This is a property that this method should have always, whatever it happens. What I'm doing, I'm saying, okay, given two random integer, max topping and an ingredient, call this test, and let's see what happens. So again, PyTest, test pizza generator. Let's run it. He found an error. So I'm continuing finding error. Because I want to pass to you that property-based testing is not only a way to test the code, but also a way to find the bug. Very simple example, of course, but how many times you forgot to check some edge cases in your code? So here is saying that max topping is saying that there is an error, an assertion error. On which assertion? On the assertion, this assertion, assert len generated pizza, blah, blah, blah. And on what falsifying, on which falsifying example? Max topping equal -1 and ingredients equal 0. I go back to my code and say, what's happening? Why? Yes, here I forgot to check for negative max topping because it's, I forgot. So we can put a check. So if max topping is less than 0, raise an error. Raise a value error. And also, I forgot to check that an ingredient is less than 0. So if an ingredient is less than 0, raise an error and make a top for max topping. Top an ingredient to max topping. Now, unit tests, why are not disappeared? Because it seems that property-based testing is so cool. They don't disappear because here my test, my property-based test, fail again with another error, with a value error, because I'm raising an exception. So I make a simple unit test. I found a bug, I fix the bug, and I'm creating another test. I'm saying that if for these particular edge cases that I found, thank you to property-based testing, so I'm trying some negative number of max topping and ingredients, I should raise a value error. I can go back to my old function, old test, and I could avoid generating a particular case. So I can say, okay, now I don't want some random couple of integer, but I want some positive integer, for example. Okay, now if I rerun, this should all be green. But I found some error. Okay, let's try to test the calculate order total price. So here, again, I have a list of pizza, and I want to sum all the prices. So this is some special type because it's not a basic Python type. It's not an integer. It's not a float. It's a list of pizza. Of course, hypothesis doesn't have a pizza strategy. So what I can do? Hypothesis give us a composite decorator. With composite decorator, I could define a function, in this case order composite, and the composite decorator pass to our function a draw function. With this draw function, I can draw, as the word say, from strategies. So what does this function? I select a length for my order, so I have an M pizza. I could put a number, but we have strategy. I could draw a random integer from 0 to 100, for example. And here, I'm building with the list comprehension a list of pizza in the range for number of pizza, and all the characteristics of the pizza are drawn from some strategy. So I'm drawn a random dough, a random number of toppings, a random price. Also, look here, for the toppings, I take the list strategy, the sampled from strategy, the sampled from ingredient strategy, and I build a list of ingredients. So it's very simple. So how can I test my function? Again, it's a very simple property, and we will talk later maybe of property. The property is, okay, calculate my price from the order. I want to be sure that the sum of my order is equal to the price from my function. Given order composite. So given random list of pizza. Let's see what happened. An error. What I found here, assertion error, okay, on which falsifying example? On an order, on an order of just one pizza. This is it's small, but it's a list with just one pizza, with a normal dough, as seems cool, with an empty toppings, and could happen. It's called focaccia, but the price is equal none. So again, I forgot to check for none value. We can fix it in our code, etc. But here I want to show you that in this example, and also in the whole example that we made today, the falsifying example is always beautiful. So hypotheses generate, I don't know, 500 couple of inputs and fail just to the list with one pizza and price none. This is not a case, but when hypotheses find a falsifying example, whatever falsifying example, try to shrink, thank you to strategies, try to shrink this example on a human-readable example that make fail the code in the same way. So here, maybe, I don't know what is doing under the hood, maybe it generates a list of 100 pizza and one have price none and failed. And so hypotheses say, okay, let's shrink it to the minimum human-readable example. And that's why it's very useful, because it's readable also by human. So we can go back to our code, fix it, and so on. So the demo for today is finished, and I hope that you have a new tool in your toolbox to not just test your code, yes, also test your code, but to find buggy edge cases in your code. So I invite you to go home, open your project that you are working on, and try to use property-based testing. The code for the demo is online. I invite you again to read the hypothesis documentation that is very well written and find all the strategies. I give also some article that I found interesting on the web. And thank you. I'm Fabio Lipreri. I work as machine learning engineer at xtream. And feel free to write me on LinkedIn or whatever to talk about software engineering, data science, machine learning. Thank you. Any question?
Thank you, Fabio. Any question? No questions?
How does it scale? I mean, like you're showing an example.
Mm-hmm.
Yeah, okay. Yeah, the question is how does this scale? I mean, you're showing an example, and usually when we see new libraries, the examples are small enough to understand. But have you tried this in a complex environment with complex classes and everything? And is it useful? Useful, but I mean, is it usable?
Yeah, thank you. You are right. It's we tried small example. Take time. In particular, when you to start to put some constraint. For example, I always put two constraints on integers, the minimum and the maximum, because I try to just put the minimum, and it start to overthink because start to go I don't know on which kind of integers. So takes time, but can be done. My suggestion is that, of course, unit test, classical fast unit test should remain. My suggestion for scaling is to put this, the property-based testing, the property-based testing tests on another, I don't know, another package or something like that, and make it run once a while. For example, for my experience, I would avoid on CI/CD, because the aim here is to find bug and maybe write a particular unit test for a specific byte. Yes, the code, the other property-based tests remain in the code base, of course, but the point here is to find bug. So maybe sometimes you run it and you make it run, you write a new one and you make it run for some minutes, not hours, not days, but for complex example, is not instant. And this is a little issue, because unit test by definition must be fast. I don't know if I replied.
And did you ever see any different results from one run to another, since it generates random? I mean,
Yeah. Sometimes happen that find a different bug in another run. There are some functions to make hypotheses more deterministic. Like you can, for example, if you find an edge case, there is a decorator that say to the test to do a specific example. So generate random example and make the specific example. So you can fix some specific example, but every time generate random combination.
If it's using random, I guess you can set a seed for the random.
Yeah, also, yes, exactly.
Any other questions?
Is there a way to use the hypothesis to actually generate some? Is there a way to use a hypothesis to generate a non-hypothesis-based test? I mean, you just generate it generates random parameters to pass to the test.
Yes.
And then can you translate them into a non-hypothesis-based unit test?
Thank you. I don't know if I get your question. For example,
let's say you said, for example, you don't use it in CI/CD.
Okay.
But let's say you start with hypothesis. Okay, great, it works. You found some bugs, you solved them, etc. But then at a certain point, you want to go to have a non-random based unit test.
Yeah.
So can you, instead of rewriting it, can you just use it to translate it into somehow a non-randomized test?
Maybe fixing a seed in some way, but you lose the advantage of having randomized input, of course, but you can fix a seed, if I remember well. But yeah, I don't know other way to use it.
Okay. Other questions? I have one.
Yeah.
So while you were explaining how to use hypothesis, I was thinking, okay, from tomorrow I will start using hypothesis for all of my tests.
Yeah.
So the question is when not to use it.
Okay. So, I like property-based testing, so I use it a lot, but it's hard. The point is when you don't have a defined property for your. Now we saw very simple example, so it's easy to find the property. It's not so easy for real life code because sometimes we have a long function, single responsibility principle, but the reality sometimes is harder than the principle. So maybe you have complex functions that do something complex, and the time you take to find some good property. So in that case, I avoid to use property-based testing and just use unit testing. But also for complex function is useful property-based testing because every function, every code, every piece of code have always one clear property, should not crash. So you can run random integer and see if crash. This is the property. So there, I don't have in mind some specific case to not to use it. I would suggest to, sometimes it's hard to use because it's hard to find good property for a function. In my experience, maybe you are all very good property finding, but in my, that's it. I don't know if I replied.
Thank you.
Yes, so the question is just maybe, sometimes you have a function and you know exactly like some edge cases. And you want to be sure that the edge cases are like tested. So there is any way to do that with this approach, or maybe it's better to do that with the classical approach? Because you want to exactly, which...
Yeah, so, yeah, thank you. So your question is, if I know some edge cases, before hypothesis discover the edge cases, I can say to hypothesis, test these edge cases?
Yes.
Yeah, you can. There is a decorator that is called example. And so you can define a given with, I don't know, 2 integer, and you can define a at example decorator, and you can specify a list of defined edge cases. And the hypothesis will run your edge cases and will generate random inputs.
Thank you. And another question.
Yeah.
So you mentioned, one of your tests was about like raising the exception, some exception, but also raising exception actually is a property. You can also write something like that in the property.
Yeah, I think you can use the classical PyTest raising exception. I separated in a different unit test because for simplicity of the demo, and because I want to take in one example the property of the output and not the exception. But yeah, you can. The property are just assertion. So everything is an assertion could be tested.
Other questions? No? Okay. Thank you again.
Thank you.
Fabio.
Thank you.
Very interesting.
Stacco.